this last day with Mukund. Mukund, we're all here.
All right. Okay, so this is the last or the third of my lectures. And like I mentioned, I was going to take it in steps because our work and or our efforts in the context of hybrid quantum systems essentially have to do with taking cavity optomechanics, taking up the good spins, and then saying what new physics emerges when we start coupling these systems together. On the one hand, I have a room temperature macroscopic system, but one with rather few degrees of freedom, or in the sense that I can, this is a system that obviously has many degrees of freedom, but they are highly resolvable. So I can isolate 1 or 2 degrees of freedom and choose to work with those. On the other hand, I have a nanokelvin temperature gas of cold atoms whose spin, whose interactions, whose multiple degrees of freedom I can create at the quantum regime with very high fidelities, 99.9% plus. I can control them, I can manipulate their interactions, I can probe it at the quantum limit, and when I do so, the measurement back action, the very active measurement, has very dramatic consequences. So in a sense, the ideal quantum system, but one that is so isolated that it's actually sometimes can be very hard to work with. Okay, so now I'm saying, can I get the scalability, the robustness, and the the macroscopicity, in a sense, of the cavity optomechanical system with the quantumness of the ultra-cold gas? How can such disparate systems even be combined? And if so, how do we do so in a way that gets the best out of both? Okay. So I covered, and we took a very atomic physics-like approach of saying we're going to start from the very basics and understand each and every ingredient and say what does it take for us to take this one ingredient and make it quantum compatible, whether it be the optics, whether it be the cavity, whether it be the mechanics, whether it be the spins, and along the way, in this bottom-up approach, what new physics comes out of it. So that's always been our approach. I don't talk about how we took that approach to the problem of mechanics and dissipation in mechanics, and we came away with some very nice insights on how to reduce dissipation and the fact that the reservoir actually is a very beneficial resource. We can get interactions that we would not normally have thought of. Then we spoke about the spins. How do we cool the spins? How do we manipulate the spins? How do we measure the spins? How do we probe the spins? What's the back action? And so now we put it all together and say, all of this is done. Now how do we actually couple the cavity optomechanical system with the ultra-cold spin ensemble? And I kind of have this picture in mind. It's a very toy model in the sense I have a cavity optomechanical system with a membrane in the middle system, the membrane being the very ultra-high quality factor membrane resonators that I spoke about in the first lecture, and that somehow this looks like light. It need not be light like I will talk about, but somehow couples to this nanokelvin gas of ultra-cold spins. And why would we want to do this? What new physics can come out of it, and how do we actually realize it and understand it both from a theoretical and experimental perspective. Okay, so all of this really started when I went to Cornell back in 2009, and then Keith saw me coming over the horizon and decided to disappear to Caltech. But we still wanted to work with each other, and I remember at some point just sitting down over coffee and saying, I work with these things. I'm a very many body physics person, quantum phase transitions, Feshbach resonances, so on and so forth, which to him was fascinating, but of course he came from a very different background, which I thought was fascinating, and so we said we should do something together. And as we started sketching out ideas, the first thing we said was, you start with the simplest ideas of saying, well, we want to cool a membrane, how about just immersing it in a nanokelvin gas? Yeah, and the gas acts as some kind of a dissipation, and then we did some calculations, and said that looks great, except there's hardly going to be any effect because you're trying to cool a 10 to the minus 9 kilogram object with a 10 to the minus 20 kilogram gas. So that's the direct coupling is probably not going to work. And then we started tossing out ideas, and then we said, you know what, it'd be really great to have a theorist on board as well. And so then we said, who actually would be interested in both these things? We either have mechanical people, or we have cold atom people. The cold atom people are all about phase transitions and delta function interactions. anything more complicated than that. Even dipole interactions are really, really hard. Okay? So they like delta function interactions, and something can be tuned. Well, great. But on the other hand, the cavity mechanical people are not usually not very conversant with cold atomic physics. And then I think almost by elimination, the answer was quite obvious. That would be here. So we both took a flight. I actually was at a summer school in Aspen, and then I talked to Keith and said, let's just go to Tucson, see what Pierre thinks. What's the worst he can do? He can kick us out. So, and then we came here, and then we went to Tucson. We went into Pierre's office, and he said, great, now let's get going. And then we went on a long drive. I didn't know what was going on. Then we came to this very room, and then we started discussing ideas of, well, what does Keith want out of the collaboration? What do I want out of the collaboration? What are the big pictures? Can we clarify some questions that we can all work on, and so on? And it came together very, very, very quickly. And it's been a lot of fun ever since. This was in 2010? Yeah. 2010, yeah. And now it's getting to the point where the experiment and the theoretical work are merging so closely that new questions are coming out just about every couple of weeks or so. And it's been very, very exciting. So the first question we said was, well, just dissipative coupling or viscous damping of the resonator is not going to work. And as an atomic physicist, to me it was all about cooling. First, how do we get this membrane into the quantum machine? I think the realization that there's so much physics to be done, even with the resonator slightly cold, that's to me at least very, very more recent. Then again, I'm kind of slow on the uptake. Back then it was all about cooling. And so we said, well, if the viscous damping doesn't work, how about just trying to use the cold gas? The cold gas is extremely sensitive to all kinds of perturbations. That's why it typically takes a heroic effort to get these cold gases to behave in the first place. But that's also a virtue, that's also a feature, in the sense that the cold gases, you can use it to study many body physics, in which case you want to isolate the system from all kinds of field fluctuations, vibrations, and so on and so forth. But if you look at the cold gas as a sensor, then it's a really great sensor. And we said, well, how about we use the cold gas to detect micromechanical motion, and there ought to be a back action from that. What kind of back action does it actually take? And that in itself is very neat, because I'm using a quantum object to measure something that's really classical, and yet is there really a back action, and can that back action be used to guide this classical object into some kind of non-classical state? So imprint quantum mechanics by measurement. And we said, well, obviously, what do we need to have an experiment like that work out? We need to be able to bring the quantum and classical object in contact or through some coupling. We need the sensitivity. The sensor has to be able to detect the mechanical object at the level of or beyond the 0-point motion, beyond quantum levels of motion, and the interaction has to be nonlinear. Maybe that's not immediately obvious, but it's very important that the interaction be nonlinear. And we said, well, one way to do that, that's basically using a magnetic dipole interaction. We can take these membrane resonators, and you can see how our understanding has evolved, because back in 2010, or this work was done in 2011, we had never actually worked with a membrane before. We knew people had worked with membranes, and there's some trampolines which you kind of asked a good friend to fabricate it for you, and then you asked them to put an nanomagnet on it, and hopefully things work out. That was our approach. And then we can shine lasers at gases and do our part. That was our approach. So that's also you can see that in the schematic. This big blob here with some big blob there, that's our mechanical resonator. Okay? And this we know very well, that's our post-condensate. And we said, well, we know that the post-condensates we work with are alkali atoms, so they have spins, and for large enough atom number, you really ought to be able to think of a collective spin. You get to multiply the spin of each atom by the number of atoms in the condensate. So at the end of the day, this is actually a significant magnetic dipole, and if you put a nanomagnet or a micromagnet on this membrane, then there ought to be a dipole interaction. Okay? So the idea is now very, very simple. Because the spins have because the post-condensate has a spin, it's actually extremely sensitive to ambient magnetic fields. And in fact, atomic magnetic field sensors are by far the most sensitive probes of magnetic fields. And the precision with which you can measure a magnetic field with a large ensemble of alkali spins is on the order of 10 to the minus 18 Tesla per root hertz. So attro Tesla per root hertz. Okay? And as a postdoc, I had worked on using that number I gave you is with thermal vapors, so large ensembles of thermal vapors. As a postdoc, I actually worked on an experiment where we had tried to use the same kind of principle, which I'll explain in a second, but with post-condensed gases to realize precision magnetic sensors which not only have very, very good spatial field resolution or field sensitivity, but also very, very good spatial resolution. The idea is, can we put the two together, and how is this supposed to work? So we have the membrane that has a magnet, and the membrane is moving around up and down because of its thermal motion or quantum motion, and so the magnet is rattling around along to the right, and that's going to create a varying or a temporally varying magnetic field at the location of the condensate, and it's varying precisely at the resonance frequency of the membrane. So we would lock in detect the field fluctuations at the membrane resonance frequency using the Bose condensate. Okay? That's the basic idea. So this is essentially AC spectrometry. And if you put in the numbers and say, is this even feasible before we go off and write a grant to do it, the numbers actually look very, very favorable, because you say, well, for a micron scale cobalt magnet, that's the magnetic moment. We can make condensates on the order of 10 to the 6, and so that's a magnetic total spin of the condensate is about 10 to the 6 4. We can park the Bose condensate about a micron away from the surface of the oscillator, and so then you calculate the magnetic coupling, which is just the dipole coupling. So there's a because this magnet is extremely tiny, spatially very localized, there's actually a substantial gradient at the location of the condensate, and as this moves around, the Zeeman coupling is essentially just mu dot B, and so we have a gradient term times the displacement of the membrane, and we end up with a term that looks like this. Okay? And you put in the numbers and you say, well, the single atom Rabi frequencies are actually in the kilohertz range, but the dissipative time scales are extremely large, because dissipative time, so the coherence time is extremely long, because the spins, because of the condensate, the atom's not going anywhere, and so the coherence time is essentially limited by intrinsic loss processes like 340 loss, but that can be on the order of 10 seconds. Okay. So how do we actually sense the magnetic field of the membrane with the Bose condensate? It's something that we can think of as it's a Ramsey experiment. That's jargon. I can just explain it very easily. The idea is that if I have a spin, let's just assume that I can model the whole condensate as one macroscopic spin, and then I can represent that as a point on this block sphere. That's this spin vector. So if the spins are all polarized in one magnetic field eigenstate, then the spin vector points up along the magnetic field, let's say. And then I put on a 502 pulse. So hopefully by now you guys are completely conversant with the spin manipulation jargon, either from Greg Fuchs' lectures or Paula's lectures. And so I'm going to put on a 502 pulse and then rotate this spin into the equatorial plane. And so now the spin is actually transverse to the magnetic field. What's going to happen is that it's going to undergo Larmor precession. Okay? The Larmor precession rate is just given by the magnetic field interaction, that's just mu b, okay, times our fundamental constants times the ambient magnetic field. So then all I have to do is that, because the coherence time is so long, unlike the NV centers or the solid state defects, this spin is going to precess above in the equatorial plane for tens of seconds. Okay? So I have all the time in the world to integrate, and what I do is to basically take the spin, watch it integrate, watch it move around in this equatorial plane for some time t, and then I measure this orientation of the spin and say how much has it rotated, how much has it precessed, and if I can measure this angle very, very well, or if I can integrate for a very, very long time, I can convert this angle measurement or this interferometric measurement into a field sensitivity, and that's just given by the angle by which it's rotated divided by the coherence time. This really is, in a sense, the precision frequency, and at the quantum limit, I can measure this angle just at the short Hausdorff time quantum limit, which is just 1 over the square root of number of atoms in the condensate. Okay, and you put in the numbers. How good is this? This is some experiments I did as a postdoc, which we are recreating in a much better way in our lab right now. This is actually a sequence of images of a needle-shaped condensate. And you can see, if you haven't seen this before, it takes a while to kind of figure out what's going on. This really you should think of as a movie, a whole bunch of frames. And you can see that there's a needle-shaped condensate which appears, then seems to disappear, comes back again, disappears, comes back again, disappears, comes back again, and so on. Okay? The atoms are always there. What's going on is that the atoms or the condensate is precessing about the magnetic field. And we are measuring its dielectric constant in this axis. Okay, by shining a probe light along this axis. And it turns out that because of the spin structure and the various Clebsch-Gordan coefficients of these atoms, if the atom has a much larger refractive index when the spin is pointing along the probe than when the spin is pointing against the probe. Meaning that if I measure the phase shift imparted by the condensate to this probe beam, that phase shift is much larger when the spins are aligned with the k vector of the probe than when the spins are anti-aligned. And bright and dark here just reflects just a measure of how large the phase shift is. So the phase shift is large. At some point, half a period later, the phase shift is small. Then the phase shift is large. And what you're essentially seeing is, as a function of time, the phase shift is large, small, large, small, large, small. So we're actually, in a kind of highly parallel sense, we're measuring the Larmor precision frequency of the entire condensate with one shot. Okay, do you have a question? No? And we can do this on a pixel by pixel basis, meaning that we can say, what is the field at this location in comparison to the field at this location? And we can actually use this kind of a movie frame to build up a 2D map of the local magnetic field. And you can see that on this color scale here, the field is small here, the field is large here, the field is small here, which is precisely what we did in this experiment, which is we created a local magnetic field in the center of the condensate, which is actually larger than in the sites. And that's exactly what this data analyzed into this 2D map reveals. And if I take a cross section or a cut in this axis, what you see is that the magnetic field is small, increases, and then goes down again. And these fields are on the order of picotesla. Okay, so if you say, well, that's good, but how big or small or how good of a magnetic field sensor is this? We have to compare with a whole range of magnetic field sensors. And there's on the, if you look at it, if you compose a map of spatial resolution on the the x-axis and field sensitivity on the y-axis, what you see is that at very, very large length scales, so centimeters, tens of centimeters, the best sensor out there is on the alkyl atomic vapors, so thermal vapors. So now you don't care about spatial resolution, then the atoms are allowed to be very, very hot. So you're allowed to have a lot of them. You don't have to worry about laser cooling, and you can sense fields, like I said, on the order of even attotesla. This is slightly outdated. You can actually get down to attotesla root hertz. But now, as you start going to smaller and smaller length scales, and you want to detect fields over smaller and smaller length scales, in the micron range, the squid microscopes had been considered by far to be the most sensitive sensors of magnetic fields. Of course, as you get to nanometer scales, the MV centers are are good, but you can clearly see that there's a trend. As you get to smaller spatial resolution, the field sensitivity decreases. There's a very clear reason for that. If you think I'm measuring some energy over some volume, the smaller the volume for a given field, the more my answer. Okay. So this is a fact of. This is just the fact that the sensitivity degrades with spatial resolution is actually very easy to understand. So in the intermediate range, for our experiment, you say, we want to be working with nanomagnets or micromagnets, where we have direct magnetic field on the scale of a micron. What is the best technique out there? The squids are out here, and even in our first iteration, which is this experiment here, which is most definitely not optimized for any kind of precision measurement, we actually beat the state-of-the-art squids. And if you actually say, what can we really do if you build an experiment that's actually geared towards magnetic sensing with most condensates, what you see is that we can actually reach 3 or 4 orders of magnitude lower than squid sensors with atomic gas microscopes. So that looks great. So we have the sensitivity, we know how to do it, we have the membranes. It doesn't take much, hopefully, to put a magnet on it. And so then we've had better understand the theoretical underpinnings of this idea. So again, just to put things in numbers, we have a condensate, we have a membrane that's flopping back and forth. For the typical membranes that we work with, the 0-point motion is on the order of 10 femtometers. And you say, well, I can put a magnet here to create a gradient on the order of 10 Tesla per meter, then that gives us a periodic Zeeman energy or Zeeman or field fluctuation of 100 femtotesla. And you say, well, you put all the numbers together and say, I can use the condensate to take 0-point motion of this membrane within about 10 milliseconds, which is fantastic. What happens when I detect it? Say, what's the measurement back action of this position detection? And this was work done by Steve Steinka and Swati Singh back a couple of years ago. And what they realized was that, let me just go through this. So this is the interaction Hamiltonian, which just comes about from the dipole nature of this micromagnet. And at the end of the day, the Hamiltonian for the condensate kind of looks like this. There's something called a back action parameter, which in a sense parameterizes the strength of the coupling between the mechanical resonator and the condensate. And the key things to note here is that it's proportional to the condensate number, which makes sense because it's a dipole coupling. The larger the spin here, that should multiply this back action parameter. It's proportional to the gradient because for a given space separation, or the gradient is the parameter that says for some amplitude of motion of this membrane, what is the resulting change in the magnetic field at the location of the condensate. And what the study basically concluded is that the way we sense magnetic fields has to do with a non-destructive or a dispersive measurement of the spins in some suitable superposition. Okay? And when you do that, the detection of the condensate as a superposition of spins then immediately projects, in a conditional sense, the mechanical resonator into a superposition of motional states. So you start out with a very nice Gaussian state, and as you measure stronger and stronger, what you see is that you can actually coax the resonator into some highly non-classical states, okay, purely through measurement back action, which is actually very, very, to me at least, very fascinating, that in a sense you can imprint quantum mechanics by using the auxiliary quantum system to measure the properties of something that's mass gamma.
Sorry, I'm too curious. What was F sub z in the previous equation?
Sorry, okay. F sub z is the z component of the magnetic of the spin operator in a sense of the condensate. So the condensate is some three-dimensional spin.
So it's an operator.
It's an operator.
Cool. Okay.
It's in a sense it's we go back and forth on this even when we're studying this work because to me at some point the condensate, even though emotionally it's a superfluid and so on, if you get to if you make n sufficiently large, you'd say, how is the, purely in terms of the spin operators or purely in spin space, how is the condensate any different from a micromagnet? Okay. Is it different or is it really the same? If I just take a superfluid with magnetic degrees of freedom and then say n is very, very large, then does the spin actually become classical? We can discuss it later.
Does it?
We can discuss it later. In a sense, you would say it should. On another sense, you say, well, the commutator actually is more and more non-zero. Okay. Fx, Fy commutes to give me Fc, but Fc is actually now a very large number. But for classical states, the commutator should be zero. So it's a question of how we are approaching it or what you're trying to do. Okay. So then we said, okay, so the last thing I want to do, the last point I wanted to make here, actually I completely indicated, I lost track of when we started.
We studied at about quarter to, what?
Okay, so I'm 20 minutes in.
Quarter to 10, so. No, what?
Wait.
Quarter past 9,
Oh.
I think. Is that when we started? Something like that.
Yeah.
The main point here was there's some very fascinating physics to be studied by this kind of motion, by this hybrid coupling, But again, it's rather it's not as easy as it seems because there are some constraints. We need to be able to get to the regime of low phonon occupancies for the memory. If not, the coupling strengths, like I mentioned, are in the kilohertz regime, and you need to counteract that. It's always a question of rates. If the mechanical system is decoding much faster than you're trying to cohere it, whatever that means, then you're never actually going to see it. Okay, all of this was really great news, and this was a job for us, for the experimentalists. There's very nice physics to be had at the end of the road, and we had to just get there. And back then we said, we'd been tossing around a few ideas of how to cool the membrane sympathetically using the cold atoms. I wish I had time to go through some of those ideas. It's always, to me, a good exercise to look at where I am or where we are at a certain project, and then go back and assess the evolution and say, could we have realized this 15 years ago? Why were we so stupid? And it's actually a very good exercise to do. At least for me, it's always been very useful. But back then we said, the only way, the auto mechanics, we looked at the literature and we said, how do people cool it? And most of them, or everybody, seem to take cryogenic cooling for granted. And then there's some little bit of cooling at the end with optics, but it's mostly cryogenic. And so that's not my favorite way of cooling things. My favorite way of cooling things is to zap them with a laser. But we didn't, just by looking at the way the community was doing things, we said, okay, we need to build a cryostat. But thankfully, we also had a whole bunch of other applications for this kind of a BC cryostat-based apparatus, including surface studies using the condensate to study things like strontium ruthenate and chiral symmetry breaking and so on. So we said, this is going to be an investment, but it's going to be a very good investment.
So the sensitivities you're quoting are sort of for DC magnetic field?
DC, to go to AC, it's actually not that hard in the sense that you have to change the measurement sequences slightly, we know how to do that. But unlike squids, right? So in squid microscopes, there's actually a very large difference between AC and DC sensitivities because as you go to low frequencies, you have a large amount of things like 1 over F noise, which are not very well understood. In the cold atomic systems, there is no such thing. So it's actually a fairly flat noise spectrum.
Okay. And so you can get the bandwidth faster than sort of the mechanical resonance frequencies.
It's purely an optical, we have to do some optical locking techniques with nonlinear optical crystals, but we know how to do that. And the bandwidth, we think we can get the bandwidth. And in a sense, that's also where we can always mix the signal down either electronically or optically. We know how to do that as well. So it's less of you might think, can we really do magnetometry at the precise frequency of the mechanical resonator? We know how to kind of do that frequency. So short answers, we can do that. Okay, so this, I think Jörg also spoke about their efforts to get a cold gas in conjunction with a condensate, and I recognize a lot of similarities. The basic idea is that we have a very compact two-chamber BEC system, which kind of looked like this. And actually, Swati Singh spent a summer or a month with us in Cornell doing calculations for this back action project. And I think she actually had a hand. She actually came to the lab and helped us move the optical table in and install some stuff. So I think so she's a really hands-on theorist. I think maybe she needed to find out what the orientation of the experiment was with respect to Earth's field or something, but she wanted to make sure she was part of each stage of the process. And this cryostat came along, took a little longer, but that's what it is. And the idea is that this is the BEC chamber. We initially cool the atoms right here, kick it over here, and out here this green kind of flange is what supports the membrane. But this green flange is connected to this stuff here, which is cooled. It's like a nitrogen container, a helium container, and this cold finger right here, which actually butts into the BEC chamber, and the condensate, and the membrane is going to be held right here. The condensate is going to be parked or optically trapped a few microns out. And this part here is largely designed by Aditya and Belinda in key swaps. So if you have any questions about how this thing actually works, and the idea also is that the one thing the VDC experimentalist hates is to vent the vacuum chamber, because he wants is for somebody to come in and say, I have this little chunk of membrane to put into your VDC chamber, which flash do I open? You don't want to do that. So the idea here is that there's a translation stage which is not shown here, that you can put a gate, you can close the gate valve, open this out, load in the substrate, whether it be a membrane or some electronic material you want to study, and then pump this stage down, open the gate valve, move the translation stage into the VDC chamber, retract the translation stage, close the gate valve, and hopefully we should be back and running within like a few days. And that's the idea. So it's a load log stage. So it's coming together actually really well. And like I said, if you have questions, ask. Okay, so that's basically what I want to talk about in the sense of this spin phonon coupling. I can talk more about the experimental details, but in the kind of the context of the winter school, I thought I'd just make the main point, which is it is actually as unlikely as it sounds. You can actually, at least you can find scenarios where you can take a quantum system and use it to probe at some quantum limit a large classical system and influence the classical system through measurement background, which sounds rather fancy, but we know of at least one situation that can actually be done, and presumably there will be. In the meantime, as we are building this cryostat and so on, we said, well, how about remote coupling? The condensate obviously likes to live in its own little chamber, but it's super sensitive to all kinds of fields, but you can't actually trick anything because, like I said, the condensate lives in this tiny little chamber. That's not the problem with cavity optomechanics. Like this can live in, like Marcus was showing, even a pressure of millibar, which really is very easy. Maybe you can even do at a pitch you can even sense the fields of some biological entity at those pressures. So we thought, well, it will also help our sensing efforts a lot, or just open up the arena of things that we can sense, if we could have somehow used this to sense some object, but then read it out with a condensate somewhere else through an optical coupling. So some kind of a remote optical coupling. How do we envision this kind of system where we have a cavity optomechanical system that's living in one corner of the lab, and then that's coupled to an ultra-cold gaseous spins in another corner of the lab through an optical fiber. How would this actually work? Okay. So again, bottom-up approach, that's always the way. Let's first look at the cavity optomechanical system, and we say, well, in the context of at least cooling, we know how to do cavity optomechanical cooling. We had lectures on that, so I won't go into that at all. But basically, you can think of it in a classical way, you can think of it in a quantum mechanical way. At the end of the day, what's the bottom line? There's a lot of groups which have, over a wide range of frequencies who have tried to do optomechanical cooling all the way down to the ground state. It's actually rather, unlike ions or atoms where we take that for granted, it's actually hard, okay? Because these membranes are not isolated. They are actually coupled to the environment, so you're always competing with large heating rates. So you can help yourself by working at lower temperatures. Like I said, you want your FQ product to be greater than 8 kTOH. So by reducing T, you can help yourselves. So that explains why most of the cavity optomechanical experiments use cryogenic pre-cooling before getting down to try to do optomechanical cooling. There's a large number of groups, many of whom we actually spoke here.
What are the dotted and the filled lines?
The dotted and the filled lines. So there are two limits to cavity optomechanical cooling, whether or not you're in the resolved sideband regime. And in this regime right here, the minimum occupancy goes as the square of this kappa over omega m. Whereas in the unresolved sideband limit, there's a slightly different limit, and those are these two ones. And assuming that this has been covered before, the limits of optomechanical cooling in the unresolved and resolved sideband. Okay, so why is this hard? So for atoms, if you say I'm going to take an ion or an ion in a trap and then do sideband cooling and I expect to get to the ground state, nobody's going to blink. going to take it. They're going to say, if you did your job right, you have to do. You have to be able to see ground state pulling, very high fidelities. Cavity optomechanical systems. The Hamiltonian always looks very nice and pretty, but you're also dealing with a whole bunch of classical or experimental realities. One of which is, for instance, the mechanical dissipation that I spoke about at length, the optical loss in the cavity or the optical resonator, and of course all kinds of classical noise sources, vibrations. In this case, the most important one is actually classical noise or phase noise in the laser. So this is the Hamiltonian, and we said, okay, first we have to actually build ourselves a very nice cavity optomechanical system, and then if you're going to interface that to cold gas, we better understand what goes into, get under the hood of this thing and understand what makes it tick. And this is a sum of terms, and you can view this as very nice physics. You can also, from an experimental perspective, at least from a building perspective, you can also view this as some kind of a to-do list. I need to get this right, get this right, get this right, get this right, and then I can worry about this. Okay, so this to me means I need to have a very, very, very good low noise laser source. Okay, so let's go build a laser which has extremely long coherence length. That's fine. This is the mechanical resonator. I spoke about that, how to make this quantum compatible, and then how to get very strong radiation pressure coupling. Okay, so first the classical noise of the laser. We built ourselves a system. So in the long wavelength, and by long wavelength I mean 1 micron plus, it's actually fairly easy to get very, very low noise lasers, but we needed a laser to do two things. One is to do optomechanical cooling, but also it had to be on resonance with the atoms that we want to couple to. So it also needs to be at wavelengths that the atom that correspond to atomic transitions. And so we went ahead and built ourselves a laser which in a sense looks like this. It's a whole bunch of mirrors pointed in seemingly random directions, but there's a method to the madness. And then you say at the end of the day, is this good enough? It's a question of what is the phase noise at the mechanical resonance frequency. That's the figure of merit. And the phase noise you can quantify also by a coherence length or a line width, laser line width. The laser line width is on the order of a few hertz for this laser, and at Cornell that doesn't mean anything. Okay, I have a light source, the line width is a few hertz. You say, well, is that a good pointer? You say, well, it's actually a lot more than that. Let me illustrate that in the sense of a coherence length. If I take the laser, the light that's coming out of this pointer, and I do this kind of a beat experiment or this interference experiment, I expect to see these kinds of fringes. No surprises there. Now, if I start changing the path length of one of these paths with respect to the other, and make this path length or path length difference longer and longer and longer, at some point, the path length difference is going to exceed this coherence length, which is a measure of how what the laser line width is. And if I exceed this path length for this diode, for this pointer by about 1 meter, then this is going to wash out. Okay, then you say the coherence length of this laser is about 1 meter, and then you say, well, then that means that the line width, the intrinsic line width of this laser is tens of megahertz or so. Okay. So for this laser, in order to see this fringe wash out, I have to take this beam right here and then send it for a trip around the Earth about 10 times. And then bring it back down, and then this fringe would wash it. Okay, that's the difference. So as random as this looks, it's actually a really nice laser. Great. So we can put a tick mark there and then say 1 down. Next, we have to build a very good cavity, like it was probably explained to you. For good optical optomechanical cooling to work, you need a cavity to be in the resolved sideband regime. That's actually rather easy to do when you're working with very large frequency resonators, but that's not what we do. Our mechanical resonators are on the order of hundreds of kilohertz. So we need a cavity that is suitably narrow in line width, and we can build that as well. Because silicon nitride, the one thing I didn't talk about in my first lecture is that as amazing as the mechanical properties are of silicon nitride, its optical properties are also extremely good. So we actually had to work very, very hard to measure the absorptivity of silicon nitride, and we could actually only put bounds on it. It's the imaginary part of the refractive index, at least the wavelengths we are working in, is less than a few times into the -7. And it's actually tricky to measure a number or put a bound on the imaginary part of the refractive index of a solid-state material at that level of precision, but we don't know what it is really. We can only put bounds. It's less than something, and that something is actually extremely tiny already. So we can essentially ignore absorption in the we can't quite ignore absorption. I would say the absorptivity of silicon nitride is not a very stringent constraint on the kind of on the optical line widths for this cavity we can realize, and we can realize cavities with optical thickness on the order of 150,000, even with the resonator inside the cavity. So this is done as well. So this is just a cavity ring down, very much like a mechanical ring down. We can do an optical ring down where we fill the cavity with light and then detune the drive from resonance and watch the photons leak out of the cavity. And so this gives us a decay time on the order of a few microseconds, or a line width on the order of anywhere from 50 kilohertz to 250 kilohertz. And in fact, for some of the studies I'm going to describe, the lower limit, getting a cavity in the result side band regime, actually makes Peer extremely unhappy, because then the spins are not doing anything. So we actually had to go and find some way to put a fingerprint or a thumbprint on the mirror and say then we can get to the band cavity regime, and then we can actually get we can test Peer's and Francesco's theories. Okay. But anyway, so this is done as well. So that's this little doohickey right here, which has a membrane somewhere inside and a very, very nice optical resonator. The mechanical element I spoke about at length. I'm just going to take for granted that we have this. Our data points are up there. QF, amazingly large, fantastic. Optomechanical coupling. The way we do this, of course, is to say we are going to have a regular fabricator cavity and put this membrane in the center. This was a design that was pioneered by the Yale group, Jack Harris. And the way we can test this coupling, of course, is that if the membrane were right at an antinode or a node, that's the last place you want to be, because there is actually no radiation pressure coupling. So you want to park it somewhere in between, and we can just step the membrane by tiny amounts along this cavity, and we can see the associated change in the resonance frequency of the cavity. And we can just park ourselves at a place where there's actually a very, very large change in the resonance of the cavity for tiny changes of the membrane displacement. Okay? And then we can quantify this optomechanical coupling parameter G, and for us it's on the order of about 10 hertz per photon. It's very, very tiny, but that's been the problem always with cavity optomechanics, that the way to enhance the coupling is to just have a lot of light in the cavity. Ideally, yeah.
How much do you step it, like 10 nanometers or something?
Well, you expect this to be, it doesn't look exactly like a sine wave, which you think it ought to look like, but in a sense it does not, because of the kind of, if you put the, it would look like a sine wave if you step the membrane somewhere near the symmetry plane of the cavity, but our cavity is not perfectly symmetric. It's a plane concave area. And the membrane is actually very close to one of the mirrors, and so it actually looks slightly more. It is periodic, but it actually looks slightly strange, slightly distorted. But it's still the case that the periodicity is given by half a wavelength, which is the periodicity of the standing wave. So we can step it by a few microns, but really all you need to do is to step it by about 500 nanometers, and then you come back to where you started.
But wait, if your cavity is not two curved mirrors, then do you run into problems because your wavefront is not flat there where you put the membrane?
It's we put the membrane actually very close to one of the mirrors, which happens to be flat.
The flat membrane.
Yeah.
So why is it not a sine function?
Okay, so it's if you
Is this because of transverse modes?
It's basically comes out of the fact that if you solve for this, it's really a couple cavity system, and if you solve for this, when if it's the symmetry plane, everything's symmetric, it is just a sine wave, but if it's not the symmetry plane, it gets more and more distorted, and it starts looking, it goes from something that looks like this to something as, so if you have let's say you have a symmetric membrane somewhere in the symmetry plane, and you move this around here, it looks like this. But if you move this, if you put the membrane here and you move this around, it actually looks like that.
So how far is your membrane from the mirror?
From one of the mirrors, the mirror spacing is about 2 centimeters,
Right.
and the membrane is about a few hundred microns from one of them. Okay. And so you put it all together and we say now I can look at the transmission of the reflected spectrum from the cavity and deduce mechanical motion. And we say, well, of course we have to characterize all the noise responses and so on. So that's a technical noise floor. This is the cavity response. As you can see, the cavity is a very, very good low-pass filter. That's a short noise limit. And you see that right at low frequencies, the cavity, we essentially have short noise limited operation. You see a lot of guff here. Those happen to be precisely the modes we are trying to study. Those are the modes. And this is for very, very low power detection. So the noise floor is about 10 to the minus 15 meters per rooters. We actually got down to about 10 attometers per rotor sensitivities.
Sorry, in the previous curve, your short noise makes me think that the cavity line width is now like 10 megahertz or something.
No, this roll off here is actually just our detector.
Oh, okay.
Yeah. This is the cavity response.
Okay.
The 10 megahertz is just our detector line. Okay, so that's the spectroscopy of the various modes that I spoke about for the membrane that's actually inside the cavity, and then we can just detune the input to the cavity from one of the membrane resonances, and then we can see all the way from room temperature we get down to temperatures of on the order of 10 millikelvin. So it all works. It's nice to see, nice to get to the bottom of a to-do list, so then you can get to your next to-do list. Okay. So that's good, and this is really not very good. I wouldn't claim that this is very well optimized. We can do a lot better, but at least now now we can actually start putting together the system with the atoms. Okay, so it's what is, in a broad sense, it's good to put things together and so on. But you say, well, what are the sets of questions, and are there at least one non-trivial question that I can pursue as an experimentalist before I go ahead and build something? And actually, it turns out there's a very, very large set of questions you can ask with such a kind of a multifaceted system. And the first thing, of course, we said was, can we actually interface this spin ensemble to this cavity of the mechanical system? The answer is actually yes. It turns out you can actually do that very, very well. Then we said, let's come back to optomechanical cooling and say, can the spins living in wherever they are enhance optomechanical cooling? And if so, what do the parameters be, and what exactly is the system going to look like? And we have an answer to that. The answer is yes. The answer that I think by Wednesday we'll actually have it on the archive. I think that's the plan for the
You
sensing.
mean it's not yet on the archive?
Apparently not. I was looking for it at 8:30 last evening. It's not there yet. The third question is, can the spin
I have a
ensemble?
former postdoc who's looking for a job.
That's what we're talking about the third question, which is, once we cool it, can we actually use the spin ensemble, because it's a highly nonlinear system, to do sub-standard quantum limit sensing of the mechanical motion? And the thing once the answer to that is yes, and the answer is yes, I think. Is that official? The answer is yes. And then what I would really like to do is to say, I know very, very well how to create spin-squeezed, highly spin-squeezed or entangled states of the spin ensemble. And can I now use this kind of a remote coupling to imprint that kind of, or transfer spin squeezing into motional squeezing? So how well can I actually do that? And there are many, many more questions, but I think we should work down the list. So 3 out of 4 in a couple of years is not bad progress, I'd say. Okay, so I'm going to only talk about the spins as a sympathetic coolant. The sub-SQL sensing and so on will be a path left for another day, I guess. But I just want to explain what is the basic idea of using spins that are remotely optically coupled to this cavity of a mechanical system as a coolant, in a sense, of the memory. First, you have to say, well, can this be done in an easier way? There's no point complicating matters just for the sake of complicating matters. But we get back to the point that cavity optomechanical cooling, especially from room temperature, is actually very, very hard because you're competing with very, very large rates of dissipation. Typically, the other constraint is that silicon nitride is this magical material that I don't fully understand, but just something that seems to have very, very good mechanical and optical properties. But that's the exception. Most resonators that you might want to study for various reasons either have very low, very bad mechanical dissipation, or they have very, very poor optical qualities. Okay. Graphene is a nanomechanical membrane that you might want to study for various reasons because it has 0-point compatible nonlinearities, but it's a lousy, it has lousy optical properties. So if you put such a resonator with lousy optical properties inside your optical cavity, it doesn't matter how good your mirrors are. Okay? The cavity itself is going to be lousy. It's going to be absorptive, and the thinness is going to be very, very poor, and the cavity line width is going to be very, very large, which means you cannot, even in principle, get to the resolved sideband regime. Okay? And if you can't get to the resolved sideband regime, you can't get down to the drop state. So then we said, can we have a way in which the spins can effectively fool this membrane into thinking that it's part of a very high thinness cavity? So in atomic physics terminology, what is the rest optomechanical response due to the coupling to the spins? That was the question we were asking. And the way this works is to basically say that we can take mechanical motion here, have this thing wiggling around, and because of the cavity optomechanical coupling, that micro motion is going to be imprinted into either phase or amplitude fluctuations of the transmitted and reflected fields. Okay, so standard optomechanics. And we are going to create a situation where those phase or amplitude fluctuations propagate over to the spins and then change their spin state. Does this sound familiar from lecture 2? I'm changing some spin property by modulating something at the at an acoustic or mechanical frequency. There's going to be an exam at the end of the day, right? What are we doing here? We take a system that's in one spin state in one vibrational band, and I said we magically moved up, and then couple it across. Okay. That magical moving up we can either do by shining another beam of light, modulating the lattice, or by shining on this atom a modulated optical field. As long as the frequency of that modulation coincides with this lattice trap frequency, I can coherently transfer this atom up one vibration band and then kick it over to another spin state. Okay. So it's essentially a two-photon transition that in this case was just by either amplitude modulation of lattice, but could very well be just modulation of a small membrane 10 meters away.
So it's not actually like a two-photon. I mean, it's not as if we're shining like two optical fields.
We are shining two optical fields, and those two optical fields are not spaced in frequency by the trap frequency. They're actually spaced in frequency by the trap frequency plus a phonon of the membrane. So it's two photons plus one mechanical phonon gives me the two-photon transition.
I guess the modulated as equivalent and we expand the mass.
But there has to be more than, typically you think of a two-photon transition in a lambda system as being in resonance when the difference in frequency between the two optical fields coincides with the difference in energy of the initial states. That won't work here. What we want is to offset the two-photon transition by a mechanical frequency. Then it's two photons plus a phonon. Or, in a sense, the atoms will absorb one photon plus one mechanical phonon and emit into the other photon. And so the atoms are absorbing the phonons. That's good. Okay, so now we have a kind of a squeegee for mechanical photons. In atomic physics, how does that work? So basically, the membranes modulate, the membranes moving around, that goes into amplitude or phase modulations, and then we have a 2-photon transition. The light goes from there to there, flips the spin. Okay, now those spins are very, very coherent, so they're very long-lived. At some point later, those spins flip back, send the photon out.
No one wants the photon.
So what?
None of them want.
None of them want the photon, but in terms of this membrane, in a sense, even if this cavity is extremely lossy, the photon came back, in a sense, a long time later. So this system, this as a whole, looks like a optical cavity with a much narrower line width or a much longer photon membrane. Is that point clear?
So why does the photon go back? Is it like spontaneous emission?
No, it's nothing spontaneous, it's all coherent. That's very important. And the photon goes back because we have a cavity here as well. Or we are reflecting the light back.
If you flip the spin, you essentially put it in an
You're-
excited state, and how does that?
No, you're not putting an excited state. That's very important. The modulation, it's standard electromagnetically induced transparency. You think of electromagnetically induced transparency as conversion of a photon into a spin wave. Not electronic excited state, but a spin wave, or okay, in a thermal gas. And that spin wave can, you basically can use that spin wave or that excitation, the spin excitation, as a memory for the photon. As a coherent process, there's no spontaneous emission, which means at some point you can undo the process and get that photon back.
So in this case, you are undoing it by shining another part.
You're undoing it in a sense by the fact that you're actually on the one hand for optical cooling, what you're doing is to simultaneously cool the spins by pumping it back. So then there is spontaneous emission. So in the context of optomechanical cooling, the atoms absorb the phonons and then they emit into electromagnetic vacuum because you're cooling the spin ensemble. In the context of sensing, rather, you want everything to be coherent. And we'll get to that, or actually we won't get to that. You can ask Francesco how that works. But here you're basically saying, I'm going to be continuously cooling the spins all the time. But they're also absorbing phonons. But from the point of view of why does that actually help? It helps because it fools the membrane into thinking that it's part of an optical cavity which has a much narrower line.
But to get back to Aditya's question of why are the spins emitting the photon back? Is it just like relaxation? They're just like relaxation.
In the context of cooling, I basically this graph here is basically showing how the spins can actually address the optomechanical response. But in the context of cooling, we are basically saying the spins, the photons come in, and then they are essentially converted to long-lived spin excitations. At some point, because of normal relaxation or because we are undoing the process by turning it back coherently, the photons will come. Okay, so what does that actually look like in frequency space? Let's go to the very bad limit where, so there's a lot of stuff going on here, but let's first consider the red curve and say we have a optomechanical system in the very, very bad cavity limit. So this is the red curve, and the blue lines are these are the sidebands. This is the input drive to this cavity. And you can see that optomechanical cooling just by in and of itself in this cavity is not going to work very well because the cavity line width is actually much larger than the mechanical frequency. But then we couple this to this long-lived spins, and what you're essentially creating is an EIT-like line shape with a resonance that we can park exactly around the blue sideband. And so now the effective optomechanical response looks like a superposition or convolution of the red curve, which is the Wave cavity response, plus the EIT line shape of the atoms, which looks dramatically more narrow than the Wave cavity response. So now we're really looking at from the membrane's perspective, we are looking at some response which has very, very good energy resolution, which can really resolve the red and the blue sidebands and so enhance cooling. Okay. And this is an example, not of membrane modulations, but actually artificial, we just artificially modulated this light at a frequency of the membrane and said, does this actually work? Can we get an EIT-like line shape? And the answer is yes, we get very nice EIT line shapes. And by changing the Zeeman energy at the location of the atoms, we can move this EIT line shape around. Which is also very nice because in cavity optomechanics, you usually have to face a compromise between saying, I want to be in the very good to do anything else, which is drive, which like back action evasion measurements and so on. I need to be able to drive this cavity off resonance. For that, I need the cavity to be in the poor cavity limit. But in standard cavity optomechanics, you're stuck with one or the other, and then you make a compromise by being somewhere in between and saying, I can't do cooling very well, but maybe I can drive it. Here, we have a way to dynamically tune the cavity optomechanical response all the way from the very poor cavity regime to the very good cavity regime by using the atoms as a tunable dielectric. So that's also very, very powerful. And, oh, I didn't realize this was it. Oh, so this is the difference between when I give a talk to experts in the audience versus giving a talk to undergraduates. So this is the concept, and this is how I explain to undergraduates. I didn't realize the slide was there. So it's the same thing, and that's the stuff, and that's the EIT judge. And the final result, when you put in all the numbers, or when Francesco and Swati put in all the numbers, the answer is actually very, very tantalizing. The answer is that from room temperature for our experimental parameters, you can actually cool the system down to the ground state over a very, very robust set of parameters, and you can look into the details in this paper or ask Francesco for all the details. But there's actually a very large, robust range of parameter space where we can actually cool the membranes that we have from room temperature down to the quantum regime. And that just really opens the world in terms of the kinds of experiments we can do. And so again, first step, we need to do that experiment. We are actually in the middle of doing that experiment, and so stay tuned. Okay, so that brings me to the kind of end of my stuff. I've taken you through why we are pursuing hybrid quantum systems. To me, this is still a very young field. Different people have different motivations. I've given you my motivation, it's actually, I think, a field that has many, many tantalizing prospects and kinds of experiments we can do, not just from the context of sensing, but from the point of view of looking at many-body physics, looking at non-equilibrium physics, looking at a whole bunch of emergent physics by coupling very, very different systems together. And I walked you through kind of a very bottom-up approach. What makes such a hybrid quantum system tick? What are the ingredients? What does each ingredient or each constraint have to satisfy? And how we can experimentally, or how we have experimentally tackled each of these challenges. Learned a lot along the way, and there's still a lot more to be learned. And of course, the people who actually do the work, the students, some of who are here, the collaborators who have made this an incredibly fun opportunity and experience for us. And thank you for your attention.
Thanks, Mukund. So Mukund is here until tomorrow, but this afternoon he's supposed to write a paper. So, so we have time for questions now, but we also have time for questions later today.
Sure.
So, anything that needs to be talked about right now? Marcus.
So, beautiful. The description that you gave in the end was essentially a single mode description.
Yes.
At least the Hamiltonian that we saw.
Yeah.
Have you looked into what happens if you include multi-modes of the mechanics?
No,
because the forest that you have is, of course,
absolutely. So the multi-mode systems, the multi-mode physics we have looked at so far is the context of the parametric resonators and how we can engineer interactions. But we haven't put that in conjunction with cavity optomechanics. But that's something, again, I would be very, very excited to do.
Well, as you look at coherent coupling between the spins and the single mode, will couple the other modes. And
Yeah, absolutely.
Yeah.
No, there's a lot of very rich physics there to be. Yeah, absolutely. So like I said, when I said more questions, there are really a very large number of questions, both theoretical and experimental, that we can access. Yeah. So I think the system is actually surprisingly powerful. You take a resonator, put it inside a cavity, you have spins, and then you connect the optical fiber. The amount of stuff you can do is actually immense.
Before we came here, we had a group meeting, and he came up with a list in the group meeting. That's the first thing he talked about. There were 13 things that he was like, by the end of the year, we are going to do these 30 things. Do them, otherwise you're off.
Well, that's the last part was for hyperbole, but the other parts were there really are a large number of things that we can do.
Yeah, I'm wondering actually how it can affect the performance. So it's, I fully agree this is certainly an asset of the system and
Yeah.
it can do multimode physics.
Yeah.
But for sensing, for coherent coupling and so on, it might be actually also destructive.
Yes and no. We have one degree of freedom there, which is we can. I showed you those images of those modes, and we have very good control of what the modes actually look like. And if you're coupling, for instance, hybridized modes, we can engineer it, or we can position it such that we have maximal optomechanical coupling to one of those modes, which by definition means we have zero optomechanical coupling to the other mode, because we are at the node of the other mode.
It's like beam shape, right? You can control your beam shapes and stuff.
No, the beam shape, let's say, is Gaussian.
Okay.
Okay. The modes I showed you have these very, very nice, quit for some reason. The mechanical modes that I'm talking about, I showed you have some very nice geometric patterns.
You disconnected, yeah.
Oh, I see. And we know that the optomechanical coupling depends on the overlap between the mechanical motion and the optical mode.
Right.
And so I can just park, I can park the cavity optomechanical mode, for instance, say at this point, which means there's maximal optomechanical coupling to this and no optomechanical coupling to this.
Yeah, but you have 5 other nodes in the environment and surrounding that will also couple.
Yeah, so we can't go too far up in frequency, because at that point it starts becoming the bug. In a sense, we have many more modes that we can control. But given the fact that we can also work at the regime where we're only coupling one mode, there's going to be soft spots in between where we can have a couple of modes or 3 modes, and everything else is infinitely far away. So I think we have a degree of freedom there. But we need to, we need to crystallize a clear question in our mind, and then find where can we work, what's best regime.
If there's time, let's talk about lunch.
Sure.
We are having similar. So we try to do to observe entanglement between the mechanic modes and the light. And the multimode character just kills everything.
Oh, I see.
And so that's why I'm asking. It's a little bit reminiscent. But if you do multimode analysis, then so if you basically take into account that you couple to multiple modes, then you can recover everything.
Okay.
Then
So that's next week's theory project, I guess. No, but we should definitely talk about it. Yeah.
It was the same for us, right? In the old chips that Garrett provided, they were like just a forest of nodes that just killed everything.
But can you use this kind of bandgap engineering to just design a cavity with just the modes you want?
Well, the problem is bandgap engineering. So far, the type of modes that you can engineer bandgap for is the frame modes, right? And the problem is the system is just too nicely harmonic. I mean, we always have other modes in the vicinity. So you can do some effective mass engineering. So basically do symmetry in such a way that we have one mode in the vicinity, you exclude a certain frequency range.
Keith also had this interesting idea of saying, can you just, even if you can't, because it's under very high tensile stress, you can't really punch holes in this membrane and create arbitrary patterns. But what you can do is do the opposite, which you can deposit tiny chunks of matter and weigh some reaches down and not the others. And so that would be another way of engineering some mode shapes that you can. The question is, will it really affect the dissipation? And if those masses are in the interior, away from the clamps, hopefully they won't change the dissipation too much.
The microwave guys don't have that problem.
Right.
Because in the microwave case, actually you couple maximally to this one mode.
Right.
Because it is maximum mode overlap between the cavity field and this drum mode, and all the other ones just you don't see because the coupling is so small. But in our case, it's this beautiful picture.
Yeah.
Your optical beam is just a point.
Exactly. Exactly.
A little tiny spot here,
Yeah.
and that means you couple to everything.
That's right.
Or you do spatial mode engineering that you fit exactly this shape.
Yeah, yeah. If you had a circular
But this
drum
you can
and
maybe even do, right?
Maybe even, exactly.
yeah.
If you use this computer-generated holograms to do exactly the right thing.
Yeah, but the cavity
It
also.
has to be a cavity mode.
Yeah, that's right.
In principle, yeah, so there is actually.
To some level, you could do that, right?
In the Netherlands, there's been a beautiful paper recently where they stabilize a cavity to an arbitrary SLM generated
that
spatial
right?
mode.
Oh, I
This
see.
was last year, so Optics Express 1 or 2 years ago.
I see.
Huh.
Actually, we should
Pip, he was a postdoc at Inventors Group. Pippi in Pinske.
Oh, Pinske?
Pinske, yeah. Pippi in
Oh,
Pinske.
yeah, okay.
He did this, yeah, exactly.
He worked on the hydrogen, ultra-cold hydrogen experiment.
So maybe I should look at that. So yeah, then just engineer.
Yeah.
More questions or comments? Again, Mukund will be here, so don't hesitate to bug him. Okay? And thank you again very much.
Together, it's been these kinds of schools. Speaking from when I was a graduate student, I've always found these to be incredible amount of fun, and the people that you meet at these schools, they become lifelong colleagues. So cherish these opportunities.
Well, thanks for coming. So let's come back 10:30, something.